My name is Dharnaja and you're watching Brain Security. This is the first video of Learn Operating Systems with me, and we're going to start off with some very basic and simple stuff, and gradually we are going to move to core concepts. Let's get started. Alrighty, we are following the free resource given by Maithili ma'am from IIT Bombay, and the first lecture says the introduction to operating systems. And yeah, so what exactly is an operating system? It is a middleware between a user program and a system hardware, right? In the most basic terms, how does the computer understand what you want to say or what you want it to do? So, operating system acts as a mediator between you and the hardware of the particular computer. It manages CPU, main memory, I/O device, card, mouse, keyboard, disk, network, everything, right? That is the core idea and the most simplest way of telling what is an operating system. Now, what happens in the background when you say you want to run a particular program? For example, if you're in your college and you have multiple subjects, right? We have Java, we have C. In the very first year, we learn about C language. So when you actually want to run that program, you just go into the terminal and compile the program using GCC, and then you do the dot slash and run the particular command, and then you get the output. But what exactly happens between these two commands internally, right? Where this is what you see on the user interface, right? On your Linux terminal or your VS Code embedded terminal. But what actually happens is the compiler translates high-level programs into the executable. Now it converts a .c file into a.out. Means a.out means assembly language. Uh, it is the language that is very close to the hardware of the system, right? You're actually dealing with registers and you're dealing with jump statements and things like that. Now, what happens? First things first, the compiler translates the C.c code into a.out code. Any language that you use to write the logic of what you want the computer to do, it is converted into assembly language first thing. Then the exe contains instructions that the CPU can understand and the data of the program numbered with addresses. Correct? Instructions run on the CPU, hardware implements an instruction set architecture that is called ISA. Okay. Instructions are directly run on the CPU, right? The operating system is like a mediator. It does not run the program, but it actually guides the way how the particular execution has to take place, right? Now, what is ISA, instruction set architecture? Now, imagine if you learned a language with your hard work, you learned about C and C++. Now, for every different system, you have to learn a new language. Or every time you deal with a new system, for example, you have a Windows laptop today, and 2 years later, you're planning to buy a MacBook. So you have to learn a new language. You need to keep learning, and if you want to switch to Android, yes, there are frameworks that you need to learn, but just get the idea of what I'm trying to say. So there is this something called instruction set architecture that the makers follow to ensure that at the base level everything is same. The core kernel commands, the core execution is the same. If you say in C, printf, print to the screen, right? So that is universally understood. That is the standard that is set. That is known as instruction set architecture. It is defined for a particular system in advance. And ISA has things like data types. It mentions the data types that are accepted by the particular system. It has integer, float, pointer, and addressing modes, indirect or direct address, memory model, privilege levels, and system instructions. That is how our IO and interrupt and system call is going to be dealt. We're going to study all of these things in detail. What is intra, what is a system call, what happens when IO happens. IO means input output operation. Yes. Next, we have CPU also consists of a few registers, example pointer to current instruction, program counter, or PC. In the most abstractful way, it is keeping the current instruction in mind. Like, okay, if you sit to study, you're thinking, okay, I just have to complete geography today. So that is something program counter does for the computer. That okay, right now I have to particularly do this task that I have written at this particular place, right? Operands of instruction, memory addresses. CPU consists of these things in its registers. Then we have what happens when you actually run a program. To run a exe, CPU fetches instruction pointed at by PC from the memory and loads data required by the instructions into the registers. Ma'am has also drawn a diagram here for our simplification. At a particular space in the memory, everything is written. The data, the program instructions, everything. Now, that is fetched. The CPU runs in three basic cycles that we must be aware of. It is fetch, decode, and execute. And this consists of one clock cycle, right? Fetch, decode, execute. Fetch, decode, execute. That is the most basic and the most core of what a CPU does. It fetches an instruction and decodes what to do and then finally executes it, right? And this happens within microseconds. It decodes what to do and then stores the result in the memory. And most recently use instructions and data are CPU caches for faster access that we already know. So that is what the CPU does when you ask it to run a particular program. But what does the OS do? OS manages program memory. The program that you write doesn't go itself and it manages your particular computer's memory. OS is responsible for that. It loads the program executable from the disk and memory. The OS manages CPU as well, initializes program counter, the context that we have to remember, and other registers to begin execution. OS manages external devices, that is read write from file or disk. All things are managed by operating system, not done. They are managed. You can think of as the hardware as the final boss, and OS is like their assistant. You cannot directly interact with the boss. I mean, you can if you have right knowledge, you can, but what the particular end system that you have, you need to interact through their manager, that is the operating system. It manages everything for the particular computer of yours. OS manages CPU. OS provides the process abstraction, right? Now, what is a process? Process is nothing but a running program. Simple. OS creates and manages processes. Is each process has illusion of having complete CPU, that is OS virtualizes CPU. Now, again, taking that manager example that I just gave previously. For example, you are the client, you are talking to this final boss through the manager. Now you have to go tell manager that I want 1, 2, 3, 4, 5, 6 tasks to be done. Now, the particular manager manages things in such a way that you think that all the tasks are given equal time and resources, and that is how they are done independently, right? That is what this line means. It time shares between it time shares CPU between processes, enables coordination between processes. OS manages memory. Manages memory of the process, code, data, stack, heap, etc. Each process thinks it has dedicated memory space, just like we saw in the CPU. In short, OS believes in equality. For itself, numbers, code, and data starting from zero that are virtual addresses. OS abstracts out details of the actual placement in the memory, translates from virtual address to the actual physical address. So you cannot actually reach the particular core resource where it's present. You just kind of know the virtual address. So as per this figure, we can see the code, data, stack, and heap all are loaded into the RAM, that is random access memory. Then we have OS manages all your devices, your mouse, your keyboard, all of that. Now, as I said earlier, where I said about fetch, decode, execute, about this one clock cycle, right? And I said over there that these are done within microseconds. We are not as fast as CPU, right? And input devices requires our input. For example, use a mouse. It would want your input. Now we cannot react or we don't work in microseconds or milliseconds, right? So the OS needs to match the pace of the hardware and IO devices, and IO processes are slow. So it also has to manage that. OS has code to manage disk, network card, and other external devices that are device drivers, everything. Device drivers talked the language of the hardware devices. Now, what is meant by that? Device drivers are for example, let us say we have different clients for this particular boss, that they are international clients. The mouse is from France, the keyboard is from Italy. Now you do need a translator in the middle. That is what the device driver is. It just translates what their needs are and kind of establishes a communication. Issues instructions to devices, fetch data from a file, responds to interrupt events from devices, user has pressed a key on the keyboard. Persistent data organized as file system on disk. Design goals of a operating system. What should you keep in mind while you design an operating system? First is convenience, then we have abstraction of hardware. You make things as simple as possible for the end user, because technology is going to be used by even an 80-year-old and an 8-year-old, right? It is not just going to be used by the core IT people or core engineers, right? It is going to be used everywhere. So abstraction of hardware is important. Also, optimum utilization of hardware is also important, because you need to save costs. Efficient uses of CPU, memory, etc. Isolation between multiple processes, right? If I'm running two processes at once, in the background, I'm probably sending a file to a friend on WhatsApp, and right now if I'm recording the video, I'm using the camera. So just taking example of these two processes, now they should exist and work independently. They should not hinder each other, correct? Then we have a little history of operating system. We're gonna read through it. Started out as a library to provide common functionality across programs, later evolved from procedure call to system call. What's the difference? We'll know that. When a system call is made to run OS code, the CPU executes a higher privilege level. They only answered it in the particular slide. A system call is doing things at a privilege level. Now, what is meant by privilege level? There are certain things that are only allowed by operating system. Why? Because you cannot just write any program and you can do anything on your system, right? Then it would be so easy to attack your systems, right? And you cannot trust something that comes from outside. If you live in a house, you don't trust everyone that comes in your house, right? You give them bare minimum access to your house. So that is what OS also does, right? If the guests that arrive at your home want something, you go and get it done for them, right? That is what OS does. And your particular system allows only OS to access those particular functionalities, and there are certain defined routes only. Evolve from running a single program to multiple processes concurrently. And yes, that is it for the first lecture of hers. And yes, I did write something about system calls, but they are there in my personal notes. I'm just going to read them. Now, system call is a program's request to OS to carry out a privilege action, because I said that earlier. What happens in the CPU? App runs in user mode. When you're using a particular device, it runs in user mode. That okay, you get this functionality that we're providing to you, and you can do whatever you want to in that given restricted space. Then, when you make a system call, right? For example, you say, okay, go fetch this file, go write this into the memory. So that is a privileged task. That is done by kernel mode. System calls uses a special CPU instruction. CPU switches to the kernel mode. OS code runs safely and CPU switches back to the user mode. There are defined entry points only. Correct? I will quickly write that down onto the screen as well, so you can take a screenshot of that. Alrighty, so these were the things that I learned in the first lecture of the operating systems. And yeah, that is about it. We will start with the lecture 2 next.